Hi, I'm presenting interval deep learning. I'm David Betancourt, and this research was performed at Georgia Tech with Rafi Mohana. The motivations for this research are various. Current deep neural networks do not have an implicit mechanism to quantify and propagate input data uncertainty. Popular approaches only quantify model uncertainty like Monte Carlo dropout. Many times this uncertainty is epistemic and we do not have enough knowledge to quantify it. As deep learning becomes more adopted in real-world applications, it becomes more important to account for uncertainty in the input and in the model. We were especially motivated by safety-critical applications where reliability in the prediction is of paramount importance. The main component of our approach is interval uncertainty. We use interval uncertainty to represent the uncertainty in the input data, the parameters, and the solution. We can assume that we do not have enough data about the uncertainties, only expert knowledge in some form about its bounds. Unlike frequentist and Bayesian approaches, we do not need to make distribution assumptions, and interval uncertainty can allow us to reason about the uncertainty in the parameters, unlike frequentist approaches. Unlike Bayesian approaches, we do not have to assume that we can interact with the world to update our beliefs. Interval uncertainty is especially useful to model high impact, low probability events. The second component of our approach is interval analysis, which is a numerical analysis method that has been around since the late 1950s. It is now used for many applications, including solving interval linear systems and optimization. The key property of interval analysis is the isotonic inclusion property, which guarantees enclosure of the range of a real valued function. And for this work, we use interval analysis to propagate uncertainty and guarantee the solution bounds. The main challenge of this work is to control the overestimation of prediction bounds due to interval dependency, which is a phenomenon of interval analysis. So going back to neural networks, we use interval analysis and the computations of a deep neural network in order to guarantee the solution uncertainty. So here we have a regression setting, which is what we will present in the experiment, and we have interval uncertainty in the inputs, in the parameters, and in the solution, which is what's shown here on this graph, on this image on the right. And for the experiments, we have an air pollution data set which has uncertainty in the features, which are sensors, and we try to predict pollutant concentration, carbon dioxide, with a deep interval neural network. We get the interval predictions here on the left, which is the green band, and we show that it encloses the underlying real valued neural network, which doesn't have uncertainty. It encloses it everywhere in the test set, and this is expected. And then for the ground truth, we have an 84% coverage, which are the blue dots. And on the right, we have the loss curves. We show that interval atom has the best performance. It tends to blow up, but we explain in the paper how to control this overestimation. Finally, we showed that if we jitter the input of a real valued neural network and use Monte Carlo dropout to account for parameter uncertainty, there's no difference if we jitter or don't jitter the input. But if we use an interval, deep interval neural network, we always get an interval solution when we have an interval input. And more details are on the paper. Thank you for your time.